already we have read the design of a CPU, mainly the two parts we have read, the design of ALU and the design of control unit. There are two approaches, the hardware control unit and the microprogrammed control unit. Now, this class will read a design of a microprogrammed CPU. So, now first we assume the programming model of the CPU. The CPU that we want to design contains two registers, an 8-bit register A 2-bit flag register F. The flag register holds only 0 and carry C flags. All programs and data are stored in a memory, and the memory size is a 256 by 8-bit RAM. Now, first we see the hardware schematic of the data flow part of this processor. So, it has the program counter, PC, MAR the memory address register, IR the instruction register and buffer. So, these 4 more registers are also there. So, in addition with A and F, the 4 more registers are 4 more registers are PC, program counter, memory address registers, MAR, instruction register, IR and a buffer. These registers are transparent to a programmer. The 8-bit registers buffer is used to hold the data that is retrieved from the memory. So, this is the this buffer will contain the data retrieved from the memory. Only a restricted number of data paths are available in this system, and these paths are controlled by the control inputs C0 through Cn. So, here this C0, C1, C2 inputs, then C3, C4, C5, C6, C7, C8, C9. And C10, C11 and C12, these are the control lines for the ALU operations. So, these 13 control lines are there in the this for this simple processor. Now, we define the control inputs. First, C0 to C9, these are the micro operations. What are the micro operations for these control signals, and what are the meaning of those micro operations? So, first one is C0. The C0 is micro operation is 0 assigned to PC, or PC is reset, or PC is clear. So, clear PC to 0. So, C0 is clear PC to 0. The control signal C1 activates the operation which is defined as PC is PC plus 1, means the program counter value is incremented by 1 or In other way we can tell that advance the program counter. This is C1. Now, C2, C5, C6 bar, C2, C5, C6 complement, it is defined as memory address register. Content of M of MAR means the content of memory address register is assigned to PC. What does it mean? That read the data from memory and save it in the PC. See here the control inputs are C2, C5, C6 bar. So, if we see that C2, C2, C5 and C6 complement, so C2 will be, this is 1, C5 is 1 and C6 is 0, that means C6 complement is 1, then the M of MAR memory address register, that will go to the program counter, that is assigned to program counter. So, it will, this line will be activated and that PC value will go. Now, next one is C3 complement C4 bar, C3 complement C4. So, this is C3 complement, control line is C3 complement C4 and operation is the program counter, value of program counter will go to memory address register. That means, transfer the, here transfer the content of the PC, that means the program counter contents of PC into memory address register. If we see that C3 bar C4 means this is the C3 complement, one input of the marks, and C4 is the memory address register. So, these two will be high, then PC value will go to MAR. See, this is 0, these will be activated. If C3 bar, if it is C3 bar, if it is C3 complement, then this value will come. Again C4 is 1, that means this value is registered to MAR. So, that operation is defined by PC to MAR. The control signal is C3 complement C4. The next one is C5 C6 complement C7, and here the content of memory address register goes to buffer. So, read the data from the memory, operation is read the data from memory and save the result, save it in buffer. Control signal is C5 C6 complement C7. We see that thing in the picture. C5 is, it is a C5 is 1. So, this line is 1, read. Then C6 complement, C6 complement is enable line. If it is 0, then it will be enable. So, C6 complement will be enable line, then it will be a read. read enable. Then C7, C7 is this buffer is activated, C7 is 1 means buffer is activated. So, the value this value, the memory, the data from the memory is stored in the buffer. This line will be activated. So, M of MAR is assigned to buffer. Then C3 C4, if we see C3 C4, C3 C4 is buffer or C3 complement C4, first we see C3 complement C4, then the PC goes to MAR, then transfer the contents of the PC into MAR. If it is C3 C4, okay, if we see if it is C3 C4, then it will be buffered to MAR. This will not be a PC, this is a buffer to MAR, and the control will be C3 C4. Then C5 C6 complement C8, C5 C6 complement C8, this is memory, the data of memory address register goes to instruction register. So, this one is read the data from memory. M of MAR means read the data from memory, read the data from memory and save it in instruction registers IR. Here it is transfer buffer transfer data from buffer to memory address register MAR. Now, C9 is F2A means this is a transfer the ALU output into register A. Now, C5 complement C6 complement, if the control signal is C5 complement and C6 complement, then save contents of register A, save contents of register A to memory, that is M of MAR to memory. So, these are the 9 micro operations that are defined by 9 control signals. These are the 9 micro operations defined for this example CPU. Now, we see the 8 ALU operations performed by the example CPU that are defined by 3 control signals C10, C11 and C12. So, C0 to C9 already we have defined, and now we see the 8 ALU operations by these 3 control signals. So, the C10, C11, C12 can take 0 0 0 to 1 1 1, these 8 possible values. These are the 8 values. Now, for each 3 bits, that one ALU operations are defined. Say 0 0 0 means ALU output is 0. This is F is the ALU output. So, F is ALU output. Now, if it is 0 0 1, then ALU output is simple the value of register R. If it is 0 1 0, then it is defined as L plus R. If it is 0 1 1, it is L minus R. 1 0 0, L plus 1. 1 0 1 is L minus 1. 1 1 0 is L and R. This is a logical operation, and this is a logical and 1 1 1 means not L, that means complement. Again this is a logical. So, these 8 operations are ALU operations are defined for this example CPU. Now, what are the instruction set implemented by this model? So, the proposed instruction set contains 11 instructions. These 11 instructions are, these are the 11 instructions. The LDA, then STA, add, subtract, ZZ means jump on 0, JC, jump on carry flag set, and logical, CMA, this is complement of register A, increment, decrement and halt. Later again we will see this thing in details. So, these 11 instructions are implemented. Now, here the first 7 are memory reference instructions and remaining 4 are non-memory reference instructions. That means that LDA, STA, store, add, subtract, jump on 0, jump on carry and the logical AND. These are memory reference instructions. Memory reference instruction means they all require a memory address. So, they are memory reference instructions. Memory reference. But the remaining 4, the complement, the increment, the decrement and the halt, they do not need any memory address. So, they are non-memory reference. Normally, all instructions can be divided into these 2 categories. So, these are non-memory reference. Now, the memory reference instructions are those instructions as I defined that they need a memory address. In this example, we have assumed that they need a 8-bit, they occupy a 8-bit memory address. They occupy, the memory reference instruction occupy 2 consecutive bytes in RAM. The first byte reserved for opcode and the second byte is 8-bit memory address. So, opcode and address, these two are the two content of the 2 bytes occupied by the memory reference instruction. Now, what about the non-memory reference instruction? They need only 1 byte of storage because they do not need any memory address. So, this part is off, the second byte is not needed, only the first byte, that is the opcode. The opcode is needed, no memory address is involved here. So, as this is a non-memory reference. Now, this supports 2 addressing modes, one is implicit and another is direct. Now, the opcode encoding for this instruction set is carried out in a logical manner. Now, we see that how this opcode instruction encoding can be done. Say we have 11 instructions defined for this example CPU, and these instructions in short form we call mnemonic. So, these are the we write the mnemonics. Then the opcode bit. Now, we know opcode bit are of 8 bit. So, I7, then I6, I5 and I4. I3, I2, I1 and I0. These are the 8 bits. Again this I3 we call this is the TC part, I2, I1 is GN and I0 is SC. TC is the type classifier. So, actually I3 will give whether it is a memory reference instruction or it is a non-memory reference instruction. Just now we have seen there are 2 type of instruction, memory reference MRI or NMRI. So, if I3 equal to 1, then it is if I3 equal to 1, then it is MRI. Otherwise, that means I3 equal to 0, it is N MRI, and that is defined as the TC, the type classifier. TC is type classifier. So, this is TC, type classifier. Now, GN is the group number within a type. Now, GN is group number. GN is group number within a type, and it has two bits I2, I1. So, I2, I1 can take 4 values 0, 0, 0, 1, 1, 0, 1, 1. Now, I2, I1, then group number is 0, 0, 1 means 1, 1, 0 is 2, and 1, 1 means 3. So, there are 4 groups for each type of instruction, 4 groups of each type of instructions. That means, if I3 equal to 0, I2, I1 can take 4 values 0, 1, 2, 3. If I3 equal to 1 MRI, then it is group can be the 4 groups, again 0, 1, 2, 3. And SC is subcategory within a group. So, SC is a subcategory within a group. So, in this way the I0, I1, I2, I3, these 4 values can be set in the for a opcode bit. This can be designed in this way. Now, the I7, I6, I5, I4 values are can be. So, we take some of the examples. Say first I take the load instructions, mnemonic is LDA. For LDA we can set these are all 0 values. As this is a MRI, so I3 equal to 1, this is memory reference instructions, and remaining are 0, 0. That means, this is a group 0, subcategory also 0. Similarly, for STA again 4, 0, this is a store, again this is a MRI, and now I can give 0, 0, 1, this is a subcategory 1. Then add also a MRI. So, I put 1. Again these are all I4 to I7, all 0 values, and this is a 0, 1, 0. So, this is a different group. Load and store are in group 0, add is in group 1, because I2, I1 is a group number. So, 0, 1 means this is a group 1. Sub is also subtract the same way. This is 0, 0, 0, 0, this is a MRI. Obviously, this will be in the same group, and this is a subcategory is different. Similarly, the jump on 0, JZ, we can define, these are all MRI, as the first 7 instructions were MRI. So, this is now I2, I2 is 1. So, this is a group 3. Now, jump on carry, again the same way I can tell that this is a 1 0 group, subcategory is 1. Now, this is a AND, the logical AND. Again this is a MRI, this is a group 3 and subcategory 0. So, up to these they are MRI type of instructions. The remaining 4 instructions were these remaining 4 instructions were complement of register A, increment, decrement and halt. These are non-memory reference. So, first what we that non-memory reference means I3, this becomes 0. So, these 4 I can put these are 0, and similarly I can give the other values, the I2, I1, I0, these are 0 0 0, these are 0 1 0, then decrement is 1 0 0 and halt is 1 1 0, and the remaining all values are 0. So, in this way we can encode the opcode logic. So, this is my opcode logic encoding. This table gives me the opcode logic encoding. In this way, for this 11 instruction, I can implement, I can design my 8-bit opcode. These are the meanings of the bits. So, the bit I3 of the opcode decides the instruction type. If I3 equal to 1, this is MRI, I3 equal to 0 is NMRI. Now, within the memory reference category, instructions are classified into 4 groups. Just now we have seen the I2, I1 value. So, these are my I2, I1 group number, that is in the opcode. These are my I2, I1 and these are decimal value. These are my decimal values. So, group number 0, 1, 2, 3 already we have seen, and if it is 0, that means this is a load and store. That is why we have put a 0 there. 1 means add subtract, just now we have seen. 2 means JZ, jump on 0 and jump on carry. 3 is AND, we have seen the logical operations. So, in this way we have defined the group number of the instructions. Okay. Now, another thing is there are 2 instructions in the first 3 groups. So, bit I0 is used to determine the desired instruction of a particular group. Okay. Now, in the same group say STA, that means LDA is 0, STA is 1. In this way we can similarly add subtract, they are in same group, add subtract, they are in same group, group 1 and subcategory I0 is different 0 and 1. For JZ and JC same group, group 2 and their subcategory 1 is 0, 1 is 1. In this way we have defined this thing. Now, how they can be, these instructions can be executed. So, the instruction execution involves some steps. We can define the what is the algorithm of this instruction, or what are the steps of instruction executions. So, step 1 is fetch the instructions. It will read, the instruction is read. Step 2, after reading it should be decoded. What instruction it is? So, decode the instruction to find out the required operation. What we have to do, or what these instructions supposed to do the operation. Step 3, if it is halt, go to step 6, else continue. Halt means you go to step 6, completed. Otherwise, continue means step 4. Step 4, retrieve operands and perform operations. Now, we know the operation, so we need some operands. So, retrieve those operands and perform operation. Step 5, go to step 1. Again the next instruction should be fetched, next instruction should be read. In this way we can execute the instructions. Normally the first step is only called the fetch cycle. The fetch instruction is normally called the fetch cycle, and remaining instructions, this is called a fetch cycle, and remaining from step 2 to step 6, these are called execution cycle. These are execution cycle. Now, how to decode the instruction? So, we see the hardware for instruction decoding. See, this is the instruction register IR. This is my instruction register. This is my instruction register. So, I0, I1, this is my I0, I1, I2 and I3. Now, I3 gives the instruction type. So, this is my instruction type. I0 is the subcategory within a group, I2, I1 is the group. So, I2, I1 is the decoder input of a decoder, and as there are I2 2-bit input, already we have seen there are 4 groups, and these groups are 0, 1, 2, 3, these are the 4 groups, and these are the defined by these 4 output of the 2 to 4 decoder. So, these are my 2 to 4. Decoder. So, in this way, this is a simple hardware for instruction decoding. Now, with this hardware and the status flag Z and C we defined initially, a microprogram to implement the instruction set can be written. So, we see some of the sample instruction sets that can be implemented. How the 11 instructions can be implemented, we can see some of them. So, first we see the instruction load. Okay, these are my instructions or the mnemonic instructions, or we can tell mnemonic. Instruction length, so this is instruction length in bytes. Instruction type, then what is the operation? So, first we see the LDA, the load instructions. So, first what do we mean by this LDA? Load, this is load register A direct. This is load register A direct. This is the meaning of this instruction. The instruction type is, we know, MRI, memory reference. So, instruction length in bytes is 2, 1 byte for opcode, 1 byte for the address, and the operation will be that LDA, so load register from memory, so M address. So, from memory the data is loaded to register A. STA is actually the reverse one. So, this is store register A direct. The meaning is store register A direct. Again, that is a type MRI. And length is 2. This is totally reverse as it is a store. So, memory is stored from register A. Now, we see add, this is the addition operation. So, again this is MRI. So, add register A, this is meaning is add register A direct. So, it will be to with which it will be added, it will be added with the memory, that means A is replaced by A plus M, one memory address register, and this subtract is totally similar. Subtract is also similar, only this will be replaced by A is A minus M, A is A minus M, that is my subtract. Again these are MRI. Now, in this way that we can write the other instructions quickly, we can write the other instructions. Again length in bytes, instruction type, then operation. So, jump on 0 and jump on carry thereof, jump type, jump on 0 flag set, this is a jump, on 0 flag, and this is a jump on carry flag set. That means if they are 1, if z equal to 1, if c equal to 1. Both are of MRI type. The memory reference instruction, so length is 2, and the operation will be, here one condition is checked, that means for jump on 0 I have to check whether the carry flag is 1 or not. If z equal to 1, then program counter is the address, else PC is PC plus 1. That means if it is 1, then jump to a new address and that value is given here. This is the value. So, that address is loaded to program counter. So, that program counter always contains the address of the instruction to be executed next. Else, that means if this condition is not satisfied, that means 0 flag is not set, then PC is PC plus 1, that means it will be a continue, that means program counter will be incremented by 1, the next address. Similarly, that JC means jump on carry. So, here also that if C equal to 1, then PC is the new address where it will be jumped, else PC is PC plus 1. So, these two are similar type of instruction, only the condition checked is 0 flag or carry flag. Now, we see the NMRI type of non-memory reference instructions. Okay, another logical operations is there, which is MRI. So, if we see the our AND, that is a logical operations. So, this is a AND register A, AND register A, and this is MRI type. Length is 2. Operation is A is replaced by A and the memory address A and N. Now, we see that non-memory reference type of instructions. So, the again this is a instruction the length, instruction length in bytes, then instruction type and the operation. Now, we have 4 instructions of type in MRI, non-memory reference instructions. One is CMA. CMA is complement register A. This is a complement register A. So, this is of length 1 byte because NMRI, again this is NMRI. Operation is, here operation is A is a complement, A is replaced by a complement. Similarly, INCA, the increment and decrement, they are of similar type, and I can write these are all one length in MRI, and this is A is replaced by this increment. So, A plus 1, A is replaced by A minus 1, and halt, again this is a 1 in MRI, and this is nothing will do, actually this is a halt. So, halt CPU, this is a halt CPU. So, these are the how the instruction sets are implemented, we have seen that portion. So, if we see the hardware organization of the microprogrammed control unit for this example CPU, we will be seeing that there is a multiplexer, this is the MPC, the control memory, and the CMDB, that actually these are the register where 3 fields are there: condition, select, branch address and control functions, that already we have seen. So, now what we have to do, that the symbolic microprogram that implements the instruction sets. So, we have only implemented the instructions. Now, we can write the symbolic microprogram for these 11 instructions, and then only we can design the this microprogram controller for the CPU. So, in this way the microprogrammed CPU we can design. So, first we have to define the instructions, we have to define the control sets, control signals and control signals for ALU also, and then that how the hardware can be decoded or the instructions can be decoded, that what is the hardware for that, and then for all the instructions how the instruction set can be implemented and what will be the hardware for that can be there. So, in this way we can design a microprogram control CPU. Now, this is the today's quiz question, that design a microprogrammed system to add numbers stored in the register pair AB and CD. This is AB and CD. ABCD are 8-bit registers. The sum is to be set in the register pair AB. Assume that only an 8-bit adder is available. So, we have to write a or we have to design a microprogram system for this problem. This is the today's quiz question. So, in the last class we have read how one microprogrammed CPU can be designed. Already we have read that how the combinational modules, the sequential modules, they can be designed, and one CPU and the part of the CPU, that arithmetic logic unit, the control unit, all these things can be designed. Now, with the advancement of technology, the digital systems has it is growing enormously, and the complexity of the system is also large. So, now all the design procedure is automated. So, today we will discuss that what so far we have read, how this can be automated using the CAD tools, and what is the current state of the art of designing the digital systems. Now, design complexity is increasing rapidly with the increased size and complexity. Now, so far in this class what we discussed the different design procedure, when the system is